Thank you very much for this this kind invitation to present our work. I'm going to be showing some work we have just started with Chris and Sue and myself on the general topic of trying to fit thermophysical properties of fluids through machine learning techniques. And since I know the audience is quite diverse, I'll start the wrong way around. I'll start with a strange example of what is of interest for most people in thermodynamics and in the general thermodynamics of fluids, and alongside some of the problems associated with what is conventional tools, and then I think that will hopefully lead into the motivation for this work. So the general topic of today's talk is about equations of state. And equations of state is basically an analytical relationship between pressure, volume, and temperature. And from undergraduate studies in chemistry, you kind of remember the ideal gas laws as a typical example of this analytical relationship between these macroscopically observed properties. More fundamentally, we can actually use a free energy as a way to calculate that relationship between temperature and density, and we'll go into that a little bit later. But basically, it's an empirical correlation of experimental observations. Well, we know a little bit about that, but in principle, we start with data, which is usually poorly spread out in phase space, and by phase space I mean the relationships of temperature, density, space. And also it has associated uncertainties with it. The mathematical form used to fit these data is anything that you want. I put here an example from Professor Vrabek's group, and this is a classical example. You can see that it's expressed in terms of the Helmholtz free energy instead of maybe pressure or any other property. The pressure would be the derivative of this function. And this mathematical function is simply a Taylor expansion in both temperature and density. The tau is the temperature, and that sigma is a sort of a density, or a reduced density. And you can see that it's just simply a sum over increasingly more complex exponents or combinations of exponents. And on the middle of the slide, you have a table with all the parameters for this polynomial function, over 120 parameters you have to choose in this particular case for this unique fluid. And then on the right-hand side, you have the real problem associated with it. You have experimental data, which are all over the place, and a function which is trying to fit something out of the information we have on the spread out information. So the problem has several aspects to it, and it's quite prone to be managed from the point of view of machine learning. Another slide, the next slide is similar in nature, but just actually aims to just suggest that this seems like an old problem. You go back to the textbooks and think about van der Waals 1873 and his equation of state. You say, well, we're way past that. We're 150 years past that. The truth is not that. This is the first paper I plucked out of Web of Science, and I have no attachments to it nor endorsements to it, but it just shows you that this is a topical subject which is still going around. These are data for PVT data, pressure, volume, temperature data for a refrigerant. The paper specifies a reasonably large, but not amazingly large number of very apparently accurate data points for the PVT relationship, and then aims to fit these data in the best way possible through a virial equation of state, which again just shows that the fit is not great, and maybe using another mathematical function they would have gotten a better fit. So there's questions here on how to fit the data and what the data looks like. So this is an ongoing problem in engineering. And actually the older engineers in the audience, they'd probably immediately recognize the slide on the left-hand side of the slide. It's a Molière diagram, an entropy diagram for steam. And this used and is still a poster, big poster in any engineering firm or any consulting firm, in which people, believe it or not, still go to this poster to find data and then go back to their engineering design. So equations of state, or representations of the PVT phase space, have been a staple of engineering for over a century, and they're still being very heavily used both in the design and optimization of chemical and biopharmaceutical processes of all types. The equations of state available are all over the place. They're based on fitting some sort of analytical expression to whatever experimental data is available. So this contribution of ours is basically tries to explore the issues surrounding the substitution of machine learning models for analytical equations of state. What can we do how much can we do with machine learning, and what can we learn or gain from this? So again, and my apologies for those who just want to hear about machine learning. We'll go into the details later on, but I still just wanted to talk a little bit about the problem itself, so we can actually get grips on what are the issues associated with our problems. So the first issue associated with equations of state is that the mathematical structure that you choose has a strong relationship to the underlying physical model, and significantly restrains both the applicability, accuracy, and even more the predictability of the equation of state. Well, so a fair question would be, well, don't we have theories? I mean, in 100 years, 150 years, we surely have advanced in terms of the theory of liquid state. And the answer is true. That is completely true. We're not completely blind with respect to where we should be looking for these relationships. I mentioned the ideal gas law as something obvious in the low pressure limit. An extension of that is the virial expansion, or is basically a Taylor expansion for medium pressure gases. Perturbation approaches were very popular in the last century to try to describe liquids as in a systematic way, to address what would be, again, the mathematics behind these relationships. And the corresponding states theory, which we'll discuss again here, provides us with some scaling approaches and makes it slightly easier to understand the different fluids just by comparing it to a given standard, or by scaling it in such a way that most fluids can be modeled with the same type of mathematical function. But in spite of the above, in spite of all this enormous volume of work, there is no accepted or universal functional form for an equation of state. As you saw at the introduction, using a sum of polynomials of different degrees and different degrees of nonlinearity, of course, somehow fits the data. And of course, the larger complexity, or the larger number of parameters we use, can sometimes imply an increase of accuracy. But in fact, this degree of accuracy, or this excess in accuracy, starts hindering the extrapolation and predictability of the model. So in other words, we're basically overfitting the problem, and overfitting is a big obstacle, because it's not trivial to understand where this overfitting is. Another thing that we'll discuss later is the fact that the data that we start with is usually very incomplete. Not only is it very incomplete, but it's also biased towards the data that are easy to measure. Room temperature, room pressure, that is reasonably easy for an experimentalist. But consider strange gases or toxic gases, or high pressure, extremely low temperatures, then it becomes more challenging. There's less data, but that doesn't mean, of course, that data should not be included with the same bias as the data that are easy. So machine learning, in view of the above, might be a very interesting high-level correlation tool. and has a potential to revolutionize the way that equations of state are developed. And in the literature, I just plucked out 3 simple examples that are starting to appear for different types of systems, for different types of conditions, and for different types also of properties. So our approach was not that of a direct application, but actually to describe or to understand the limitations. So for that, we wanted to show a proof of concept that we could generate a machine learned equation of state with reasonable ease, and to try to understand what were the limits and what we should do to improve or change our approach towards producing these equations of state. We wanted to quantify the effectiveness of machine learning techniques to separate the hype from the practice. And for that, of course, we would need a large set of experimental data. I mean, that would be the logical starting point. Let's start from the same point. But as I mentioned, that starting point is flawed. Is flawed because the data are not self-consistent. Is inconvenient because the data is not the data points are not equally spaced around the whole phase space that we would want it to be. Furthermore, the whole point, as we all know, of machine learning is to manage large databases and to obtain relationships by the sheer number of the databases of the database allowed. So that's not usually the case. If you start focusing on let's say we want an equation of state for alkanes, or we want an equation of state for biodiesels, you're starting to limit your family, and you're starting to limit the amount of data that are available. So when I'm saying that, I'm saying that we might have 100 data points instead of 10,000 or 50,000 data points, which would be a nice starting point. So we decided to change the approach, and instead of actually using experimental data directly, we thought about generating pseudodata. We do that by starting with an existing equation of state, which is a state of the art equation of state, which we know is good. And we use it to generate pseudodata for a large family of fluids and conditions. This allows us to scatter the data, to avoid the uncertainty in the experimental data, and to be able to generate as many data points as we want. But also it has the great advantage that we know the answer. We know that the data was generated by the equation of state, so the original analytical equation of state is the correct answer. Whether this is the property of a fluid or not, it's recognized that it's irrelevant. For our exercise, that data set is the answer, is the exact data. And we want to see if with a machine learning approach, we can reproduce that data. Another thing we wanted to discuss a little bit was this balance between the possibility of using artificial neural networks and using Gaussian process regression. It's like common knowledge, and I put this in quotes, that Gaussian process regression would be ideal for regressing experimental data, because you need less of the data and you can manage a little bit more the spread or the error. And the question is if this is true, and if this is applicable to this particular case. And how about questions about accuracy and capability to fit the PVT data themselves? And what are the resources we would need in both of these cases? Our benchmark data is that from the SAFT equation of state. And so again, I reiterate that what we want with this equation of state is not to question its validity or its usefulness. It's just to recognize that this is a simple way, a simple systematic way of producing a large pseudo database of compounds, which then we can use as our experimental data. We chose the equation of the SAFT equation of state, which stands for statistical associating fluid theory, for no particular reason other than we're familiar with it, and we have worked a lot to develop it. We could have used anything, to be very honest. The interesting thing about the SAFT equation of state is that it is a description or a theoretical description of an underlying force field. And the force field is a Mie or a Mie potential, which is you could think of it as an extended Lennard-Jones fluid, where the repulsive exponent is also one of the parameters. The molecules in this model are defined as seen in the right-hand side cartoon as chains of spheres, where M defines the number of spheres associated with a molecule. A length scale is associated with a size, an approximate size of the beads, which is really related to a density. Epsilon relates to the general energy of each one of these, or scaled energy of each of these spheres. And lambda is, as I mentioned, the repulsive exponent, which talks about the range of the potential and also the hardness of the potential. So hard molecules like perfluoroalkanes would have a larger value of lambdas, while softer molecules like water, for example, would have a lower value of lambda. All surrounding, for example, numbers like 12 or 14, which we're familiar with the Lennard-Jones model. And notwithstanding this, the comment that is just an equation of state, I just want to make the notion that it does a rather good job. I mean, on the right-hand side, you see a parametrization for the phase diagram of hexane, and you see the equation of state as a solid line experimental data, smooth experimental data as a black lines, and MD of the potential as a red line. So there's a fairly good amount of consistency in the model and in terms of what it does. The model, of course, is a very coarse-grained model of reality. Molecules are not simple spheres, and there's an underlying assumption that the model is somehow coarse-graining the actual atomistic representation of molecules. And so a molecule like nonane, for example, would be modeled as a collection of 3 beads, and each of these beads is characterized by a value, as I mentioned, the size and energy values with sigma and epsilon, a lambda discussing the range of the potential. So in principle, there would be 4 degrees of freedom for each particular molecule or fluid. But one thing that we can do with a model like this one is invoke a conformal behavior or the corresponding states principle. And if that, we can actually reduce the variables with respect, and the general variables with respect to the energy scales and the distance scales. And the right-hand side, you see expressions in which, more or less familiar expressions, in which we use a temperature and scale it against epsilon. We use epsilon and energy and volume to scale pressure, and we use volume to scale the density. So in principle, really, there's only 2 degrees of freedom. One is the value of M, how many spheres we're talking about, and second, lambda, which describes the general strength of the potential. Think of it, if you want, for a Lennard-Jones fluid, M would be 1, lambda would be 12, and the fluid will be completely described. There would be only one fluid to look at and one family one PVT space. So the problem becomes a little bit more complicated because we have now basically those two complete parameters that define a fluid, apart from, of course, a whole PVT space that we want to fit. So talking about that, let's talk again a little bit about the degrees of freedom. If we look at a phase diagram, and we'll have to excuse my cartoonish drawings on the right-hand side, but I couldn't find one that really did a good job. What I'm doing on the right-hand side is showing what the phase space looks like, and just reminding you a little bit about basic thermodynamics. For a pure component, we have in a temperature density diagram. We can easily recognize a one phase region and the two-phase vapor-liquid equilibrium region, which ends at the top at a critical point. And it's interesting to point this difference out because there are differences in the degrees of freedom that we see in both of these in these three regions. In the bottom cartoon is a pressure temperature plane in which the two-phase envelope is seen actually from the side, and it just collapses into a line, which again ends at the critical point. But basically, the discussion is that these three things, the critical point, the two-phase region or the vapor-liquid equilibrium region, and the one-phase region, which spans both the vapor, the liquid, and the high-density gases, have different degrees of freedom and therefore are defined in different ways. For the critical point, once we define what M and lambda are, the critical point is defined. Again, it's useful to think about the ideal, the Lennard-Jones system in which there's only one degree of freedom and there's only one critical point for the Lennard-Jones system. If we're talking about vapor-liquid equilibrium, temperature becomes the relevant scale. And for each temperature, we will have a vapor pressure, we would have a saturated liquid and a saturated vapor data point. So there's only really one degree of freedom, but there's three outputs that can be obtained from that one degree of freedom. And if we're in the one phase region, in the green region, then it becomes the other way around. We have to define at least two properties. In this case, the two could be temperature and pressure. And for that, we would get only one answer, which is the density. So of course, it would be impossible or very impractical to run a single neural network that would do all this at the same time. So it makes sense to divide the space into these three different regions and discuss in these three regions what are the nuances of the machine learning strategies. As I mentioned, we'll look at two things. We'll compare two things. We'll compare standard artificial feed-forward neural networks with Gaussian process regression. We played a little bit with the number of layers needed. These problems seem to be relatively simple, with 3 layers being more than enough for our needs. We used the stochastic gradient descent optimizer, again, with no particular bias, it just simply worked very well. In general, and I'll discuss a little bit more later on, we used 80% training data and again, and 20% for validation. Again, very common selections, and PyTorch to actually do the regressions. We also used MATLAB if someone wants to comment a little bit on that later on. For the Gaussian process regression, again, we did basically some things very simple. We kept things simple. We had a linear combination of radial basis functions and a kernel for each dimension. The reason for that was basically that we wanted infinitely differentiable models. Not so much for this particular application, but in general, from the equation of state, once you have PVT data, or the Helmholtz energy data for that matter, you can expand that and find derivatives which are meaningful. For example, the derivative of the Helmholtz energy with respect to volume is pressure. The second derivative are other thermodynamic functions, et cetera, et cetera. What we did see, of course, and as it will become apparent later, is that with the computational effort increased enormously for the Gaussian process regression. And so we tried to keep the number of data points rather small as compared to the artificial neural network. And that's an interesting point to highlight. Another thing that's interesting in this type of problem is that the data that data reduction can be performed. We can regularize data, and for that we can actually use the physical nature of the problem to include as much theory as we can into the problem to make it simpler. This slide probably explains it in the best way possible. If you were going to look at the different families of phase diagrams that you would obtain for different length scales or different number of spheres for the same lambda, you would see that the diagrams are very different one to the other, and span very different values of density and temperature, even when we reduce them, even when we express them in reduced units. However, if you decide to scale things with respect, further scale things with respect to the critical temperature of each fluid, and for example, consider the segment density instead of the absolute density of the molecule, we see that the diagram on the right is much simpler in terms of the range of both the densities and the temperatures which we explored. So that, of course, improves significantly the effort required from the different methods. So let's start with the meat of the results. Well, the first one is a critical point. The critical point is an interesting result. As input, we use basically the different types of fluids, and output we get a pair of temperatures and pressures. We compared both the accuracy of the ANN and Gaussian processes, and they were both amazingly good. You see the R squared for the case of the critical point just simply could not be better. And on the left-hand side, you have the predicted critical temperature as opposed to the equation of state critical temperature, or the exact one. And you see an actually a perfect fit. And the distribution, the histogram distribution on the top in blue or purple, depending on your eyesight, is the distribution of data points along that line. For Gaussian process regression, we also looked at, I present a different way of showing the data. And here I'm placing it as a heat map, where green signifies almost 0% error, while the more yellowish colors indicate that there is some sort of discrepancy in the numbers. It's very interesting to note that the errors are larger at the corners, are starting to become large at the borders of the phase space that we considered. And this is really significant, and it's important. It's important for us, because what it means is basically that these models are doing a good job at interpolating the data. And of course, in the edges of the problem, there is nothing to interpolate to, right? On the other side, let's say below 8, there is no data point. So the system cannot, we cannot make any inferences on what the results are going to be at that size, at that point. Or for example, think of what happens at m less than 1. M less than 1 means nothing. M is just one sphere, and less than one sphere, there's nothing. So there's nothing to the left of that. And there's no real consistent way of trying to improve the values at those limits. So that's an interesting and a dangerous and interesting observation. The other type of results we had are the vapor pressure. Remember that there's now a change in the degrees of freedom. In this case, we specify a temperature, and from the temperature, we get the pressure and the densities of the liquid and the vapor. If we do a standard regression of pressure, we would, with an ANN, we would see a result that looks very much like the ones on the left-hand side. From the numerical point of view, it looks very good. R square is high. Everything looks nice. But if we start looking a little bit more and zoom in at the detail of the low pressure errors, we start seeing that it doesn't look that good, and that there's a lot of dispersion. And of course, a problem associated with this is that pressure in fluids spans an exponential range. Think of the pressures, the vapor pressures of water, which go from 10 to the -3 bar all the way to several megapascals. So the range of the properties is very large. In this case, it's very convenient to use a Clausius-Clapeyron equation, which suggests that instead of using pressure and temperature, we should be using the log of the pressure, and instead of using temperature, we should be scaling against the inverse of temperature. So putting that information, putting that information regularizes the data, and it doesn't look apparent by the R-square that we have improved something. But if you look at the dispersion plot, you see that everything behaves much better. These are two examples of vapor pressures where the prediction from the neural network is a straight line as compared to the pseudodata, which are the crosses. And you can see that there's a very good fit across the board for vapor pressures for both simple spheres and actually, for example, chains of 10 spheres. So we go all the way from monomers to almost polymer-like behavior and all types of ranges of interactions with the same artificial neural network. Now, this is quite impressive from the point of view of an equation of state. If we look at the at the densities, we see more or less the same very nice agreement. But take a look, we zoom in a little bit, and we see that again in the corners, in the corner cases, n equals 1, lambda's low, and we start seeing small mistakes. And this again is the same discussion I did with the GPR and in terms of the failure of interpretation at these schemes. So what did we learn? Well, with a VLE, we learned that we had to use a very large data set for the ANN. However, the fit was really good. We didn't have any problems fitting. And the other thing that we learned, and it's important, is that the good model performance described by common statistical indicators does not guarantee the correct VLE shape. We actually tried to run this with Gaussian processes. We got good numbers, but when we looked at the VLE shapes, they weren't good. Even when we included enormous amounts of data points, it simply didn't work. So that was a strange take-home message. Supercritical densities did not pose much of a problem. Again, we used artificial neural networks with a reasonably simple fitting procedure. We got what we thought was excellent agreement, and we were able to predict, for unseen data, for example, which were within the phase space, we obtained a very good fit. So as a conclusion, we basically came up that we could use ANNs, or Gaussian process regression, to correlate and predict thermodynamic properties based on a few simple molecular descriptors. And the use of what we learned was that ANN actually showed a promise as a viable technique for correlation, actually above what we saw for Gaussian processes. Now, interesting thing is that the results are as accurate as the baseline equation of state. Just incidentally, I might mention that since we also developed the original equation of state, and it took us over 5 years of several postdocs and a lot of work to actually get to the point where the equation of state is right now. While a neural network that we used basically took us, I would say, weeks, just simply because we started from scratch, but we could have done it in days. We could now do it in days. So that is an amazing change. That is an order of magnitude change, and the quality is basically the same. Of course, the application I'm showing you is completely useless. We already had the equation of state, so what's the point? But we learned limits. We learned how to use these methods. And we understood that the essence of the requirement of the machine learning to interpolate data, and the reason why we need the spread and quality of data is paramount. Another thing that surprised us is that the Gaussian processes didn't fulfill its promise, which we would have expected a better result from this, and we're still thinking about what this actually means. The real challenge, of course, is now not equations of state over fluids, but actually try to generate pseudodata. And we're working on that. I'm just mentioning a few things that we're working on. We're working on generating pseudodata with classical molecular simulations. That way we can fill the phase space in as much and as densely as we want, and use this data then to generate more accurate equations of state. And the interesting thing is that we're not limited then to PBT data. We can certainly do the same thing for equilibrium properties, transport properties, diffusion, interfacial tensions, and building bridges where the theory is still in its infancy. So these are still work in progress, and I'll just mention it because I know people in the audience are interested in that, and I would be happy for them to um, to tag along and to discuss these things, maybe offline or whatever. So my acknowledgement to Chris and Sue, which did all the work, and I'm finish here to leave a few minutes for questions. Thank you very much.